The topic is series. We already learned about an infinite sequence. It can be represented with a sub 1, a sub 2, a sub 3, and so on. An infinite series is the sum of the sequence, and it can be written a sub 1 plus a sub 2 plus a sub 3, and so on. It is denoted by the summation as n goes from 1 to infinity of a sub n, or simply the summation of a sub n. So we call that series. The example I have begins with 1/2 plus 1/4 plus 1/8, and so on. The nth term for this sequence of numbers is 1 over 2 to the n. And it is a series written like this because we are adding up the terms. So we could also write it in summation notation. So we have n going from 1 to infinity of 1 over 2 to the n. Of course, we could not literally add up all the terms of an infinite series. So what we do is we have the approach of taking partial sums. So if we just start simply at the beginning and take the first term, it is 1/2. So we say the first partial sum is 1/2. The second partial sum will be adding the first and the second terms together, which is going to add up to 3/4. The third partial sum is the sum of the first three terms, which is 7/8. And we'll do one more. The fourth partial sum, as it is called, is 1/2 plus 1/4 plus 1/8 plus 1/16 for a total of 15/16. So here we've selectively chosen the first four partial sums to examine. This also creates a sequence of its own. So every sequence has every series has a sequence associated with it, and it is called the sequence of partial sums. So we can represent the sequence of partial sums with this notation. Because it's a sequence, we have this grouping symbol, and here are the sums. The first one we have was 1/2, then 3/4, 7/8, 15/16, and so on. If the sequence of partial sums has a limit, then that limit is called the sum of the series. And it is convergent. If the sequence of partial sums, S sub n, is divergent, then the series is called divergent. An interesting approach to examining this particular sequence of partial sums would be to notice that each sum that we found was getting closer and closer to 1. So if I look at those sums, they are 1/2, 3/4, 7/8, 15/16. We'll take those and we can rewrite them as 1 minus a half, or 1 minus a quarter, or 1 minus an eighth, or 1 minus a 16th. So we could look at them that way. And that is actually a nice expression to write our sequence in our nth term for the sequence. So notice that every term we're going 1 minus, and then it's a fraction where the denominator is 2 to the n power. So I can write that as 1 over 2 to the n. So that is our nth term for the partial sums. And you could take the limit on that as n goes to infinity. So the limit as n goes to infinity of 1 minus 1 over 2 to the n is very easily evaluated. The limit as n goes to infinity of 1 is 1 minus the limit as n goes to infinity of 1 over 2 to the n is 0. So the sum for this sequence is 1. Therefore, the sum of the series is 1. The series has a sum, therefore it is considered convergent. Let's go ahead and look at a special series that will be very useful. It is the geometric series. The geometric series has a formula for the nth term that we can use right away. The series as n goes from 1 to infinity of a times r to the n minus 1. R is known as the common ratio of the geometric series. And if I want to look at each individual term to begin with, I would start with letting n equal 1. 1 minus 1 is 0, so r to the 0 is 1. So our first term would just be a, because r to the 0 has gone to 1. Then I'm going to add the next term when n equals 2. So when n equals 2, 2 minus 1 is 1. We'll have r to the first power. So a times r will be the second term. Every successive term then will have a higher power on r. So the next term is a times r squared, then a times r cubed, and so on. The series converges if the common ratio, if we take the absolute value of the common ratio and it is less than 1. If the series converges, we could also find the sum of the series. The sum of a geometric series is its first term over 1 minus the common ratio. So it's important that you think of a as the first term in this situation. So you might want to write first term over 1 minus r, if that helps to remember. And then if you find the absolute value of r is greater than or equal to 1, then the geometric series is divergent. Example number 1. 8 minus 12 plus 18 minus 27 plus 40.5 minus, and so on. In order to determine if the series is geometric, we can check the ratio of terms. You want to look at two terms successively, and you take the second term, divide by the preceding term. So the ratio between these two terms is negative 12 over 8, which reduces to negative 3/2. Is that true of the next two terms? I could examine negative 12 and 18. So I'm going to take 18 and put that over negative 12. Does that reduce to negative 3/2? So you want to check to see if it's geometric to begin with. If it is, we know what to do then. We have our formula for geometric series. Let's set up the series itself. I'm noticing that the first term is, I'll write a sub 1, the first term is 8, and we have our common ratio of negative 3/2. So write the summation as n goes from 1 to infinity of 8 times negative 3/2 to the n minus 1. And I'm simply following the formula for geometric series. So that is the series written in notation form. Can you answer the question, does the series converge or diverge? Do you remember what to check? Go back to the common ratio. When you take the absolute value of it, is it less than 1? Since the absolute value of r, which is the absolute value of negative 3/2, is 3/2, and that is not less than 1, then the series diverges. And since the series diverges, we do not find a sum. Let's look at another example. Look at 9 plus 6 plus 4 plus 8/3 plus 16/9, and so on. Check for a common ratio. The second term divided by the first term gives me 2/3. The third term divided by the second term also gives me 2/3. I'm concluding that the common ratio is 2/3. To set up this series, I'm going to say n goes from 1 to infinity. The first term is 9 times 2/3 to the n minus 1. Again, that's just following the formula for geometric series. Now, I'm going to look at the common ratio to determine if this series converges or diverges. The common ratio is 2/3. Since the absolute value of r, which is the absolute value of 2/3, equals 2/3, and that is less than 1, the series converges. Once we know the series converges, we're expected to find the sum of the series. The sum of the series is always the first term divided by 1 minus the common ratio. I'm a little weary of putting a sub 1 because the first term could be denoted as a sub 0 in special situations. So remember that that's the first term, which is 9 over 1 minus the common ratio of 2/3. And what do you find that to be? (27). It's important to realize that we're not actually adding an infinite number of terms. We did not sit here and add up terms to infinity. Rather, we take the sum of as many terms as we need to so we can get as close to the actual sum as possible. So how do we get as close to 27 as possible? So what you could do to understand this better is look at it on your calculator. So if I take out the calculator and I enter the series into y sub 1, there it is, 9 times 2/3 to the n minus 1. I'm going to do this on the home screen. So I'm going to hit second, quit, and I will choose the math menu. So math menu, choice 0. So you can scroll all the way down to see where that is, or you could scroll up to get there quicker, or you could hit 0 to get there the quickest. So I'm choosing summation, and on the newer calculators, you can get a nice pretty print version. So I'm going to type in x goes from 1 to 1. So I'm just going to look at the first term of my partial sum series. And the function, we're representing our series with a function in y sub 1. So we're going to go to vars, y vars, function, and pull y1 out to use in the home screen. And when I do that, I get 9, which is hopefully obvious to you that the sum of the first term would be 9. It would probably be more interesting if we added more terms together, and obviously we were trying to see how this looks when we approach the proper sum of 27. So if you hit second enter, you will get your entry back up, and you can arrow left to change how many terms we're going to do in this partial sum. Let's do 5 this time just to make it more interesting. We actually, we got closer to 27. We're at 23.4 repeating. And we have the ease of the calculator to keep playing with this. We can choose as many terms as we like. We can choose sufficiently many terms so we can get as close to 27 as we like. So hit second enter, and you can use the left arrow. Let's put in 10. Now we're creeping up on 27 pretty well. That number may not be satisfactory, so we will choose another, and you could choose do this as much as you want. If I choose 15, I'm now at 26.9. You could tell the sum is like slowing down. It's getting closer to 27. Second enter, I'll put 20 in there. And now I'm at 26.99. I could put 25 in there. And we're getting right on top of 27. So this is we're mimicking the notion of choosing sufficiently many terms as we like to get as close to the actual sum of 27. One last observation on the calculator that can be useful is go to y equals once again, arrow down to y sub 2. In this venue, you can go to math and pull up the summation. So I'll choose math 0 for summation, and I'm going to enter it in as a function. So I'm going to enter x goes from 1 to x because we don't want to put a limitation on what we're finding with regard to the partial sums. And we'll choose vars, y vars, function y1. And then you can use the table feature to take a look at partial sums even faster. I'm going to check my table settings. So I'm going to go second window to look at the table settings. I'll start at 1, and my delta table can be 1. However, it might be more useful to make delta table larger to see it approach the sum of 27 even faster. The table feature is underneath the graph button, so I'm going to hit second graph and give it a moment to do all the calculations. You can scroll up and down on the table. You can scroll up, which will be a problem for your summation. When you scroll down, you start to see, you can see this is our sequence right here. Our original series was listed out, 9 plus 6 plus 4, and so forth. And to the right of that now are the corresponding partial sums. Here's the first partial sum, the second partial sum. Here's the third partial sum of 19. I think we got the fifth partial sum on the calculator a moment ago, 23.444. Here is the 10th partial sum. And it takes longer when you scroll down one at a time because the calculator is doing all this calculating. So you may want to make your delta table bigger to watch it approach 27 even faster, or some other sum for some other math problem you're working with. But please practice this on the calculator, because if you have the calculator in hand when being tested, it can greatly help you. All right, that wraps it up for this part of the section. Watch the next video to see the rest of the notes for section 2. Thanks.